Hi, my name is Mikko Suvanto, and this is the MOSOMIC MEMS Microphone Guide. In this episode, I dive deeper into the electrical and acoustical testing of MEMS microphones. Stay tuned. This series is sponsored by Innovating Technologies. Electro-acoustic testing is typically done by exciting the microphone with an acoustic input and at the same time measuring the output of the microphone with some sort of signal analysis equipment. However, in the case of noise measurements, the microphone is typically not excited. On the contrary, any excitement is avoided as much as possible. A typical setup looks something like this. A calibrated speaker is used to generate the acoustic test signals that the microphone, the device under test, DUT, receives. The properties of the speaker, such as frequency response, distortion performance, and self-noise level, must be suitable for the measurement. A wideband speaker is needed for frequency response measurements. A one-way speaker or a speaker with coaxial elements should be used when the distance to the tested microphone is short. This improves the accuracy of the sound field at the DUT. The speaker may also be an artificial mouth of a HATS device, a head and torso simulator. The speaker gets its input from an audio analyzer. The signal is amplified with a power amplifier. The DUT is placed at an appropriate distance from the sound source. The distance may be specified in the test description, for example 50 centimeters. Next to the DUT is a reference microphone. It's typically a high-quality, high-performance microphone with a low self-noise, flat frequency response, and good distortion performance. The reference microphone is used to verify that the sound input to the microphone during the test is as specified, especially what comes to the sound pressure level. The reference microphone must be placed very carefully so that it's exactly the same distance from the sound source as the DUT. On the other hand, the reference microphone should be placed so that its acoustic influence, for example reflections, on the DUT is minimized. A dedicated, well-maintained and frequently calibrated sound pressure level calibrator is used on the reference microphone to set the measurement sound pressure level to exactly the right level. A typical calibrator feeds a 94 dB SPL 1 kHz signal to the reference microphone. The DUT microphone, the reference microphone, and the speaker are all connected to the audio analyzer. Like I said, the output of the analyzer feeds the speaker via the power amplifier. The output is regulated so that the DUT receives exactly the right sound signal what comes to sound pressure level and other parameters. The regulation of the speaker output is done with the help of the signal received from the reference microphone that receives the same acoustic input as the DUT microphone. A key function of the audio analyzer is to also monitor and analyze the output signal of the DUT and output the results of the analysis as the test results. Sensitivity and SNR measurements are usually done using a 1 kHz test signal, but some other tests may be done using other frequencies. In measurements that measure a parameter throughout a range of frequencies, such as frequency response, the measurement is done by doing a frequency sweep or by testing a number of discrete frequencies and then combining the results into a table or a graph. Frequency responses are often measured for the audio frequency band from 20 Hz to 20 kHz. Sometimes a narrower frequency band can be used, for example from 100 Hz to 10 kHz. The test signal level is typically 94 dB SPL, which is equal to 1 Pascal acoustic pressure. This is the standard test signal level for MEMS microphone sensitivity and signal-to-noise ratio measurements. In some cases, for example in distortion measurements, the sound pressure level may be significantly higher than 94 dB SPL. 130 dB SPL is a fairly common level in acoustic overload point measurements, but there are MEMS microphones that can handle up to 150 dB SPL, and to measure them, the measurement level must naturally be as high. Normal laboratory speaker systems may not be able to produce sound pressure levels this high, especially if the measurements are done at lower frequencies. For the distortion measurement to be meaningful, the distortion of the test signal must be significantly lower than the distortion level of the microphone at that sound pressure level. Some distortion measurements are done at lower frequencies than 1 kHz to test how well the microphone can handle lower frequencies contained in, for example, music. The lowest measurement frequency can be, for example, 200 Hz or even lower. Producing very high sound pressure levels at frequencies this low is not easy, and the sound reproduction system, the amplifier and the speakers, must be specifically designed for the task. To help achieving a low distortion, high SPL test signal, and to save the ears of the test personnel and the nerves of other people within 50 meters, a closed enclosure, such as an adiabatic chamber that houses the speaker or multiple speakers, and the DUT and the reference microphone may be needed. Phase measurements put stringent requirements on the placements of the different acoustic components in the measurement system in relation to each other. Like I mentioned in the previous episode, having the same distance from the sound source to the DUT and the reference microphone is critical. The higher the measurement frequency is, the more accurate one must be with the placements. At 1 kHz, 1 degree corresponds to a distance difference of about 1 millimeter. In other words, a 1 degree phase measurement accuracy requires that the placement accuracy is well below 1 millimeter. At 20 kHz, all it takes is about 1/20th of a millimeter of location inaccuracy to cause a 1 degree difference in the measurement result. The use of jigs is a good way to help achieve good repeatability and high accuracy in phase measurements. A jig should be used to help with the placement of the DUT and the reference microphone. The jig system can be designed to include also a place for the sound source. Reflections are another factor that can affect the accuracy of phase measurements. Reflections can be caused by the reference microphone that must be placed close to the measured microphone, or other objects or walls near the measurement setup. The other objects can be, for example, the jig or stands used for building the measurement setup, tables or other furniture, walls, and so on. Reflections from walls can be avoided by doing the measurements in an anechoic chamber, where the walls are designed to not cause reflections. Another way to avoid reflections is to do the measurement in a large enough space, so that the time difference between the sound signal that reaches the DUT directly and the reflected signal is long enough. Sound reflected from distant walls or objects is also weak, because the sound gets attenuated as it travels, so the reflections are less likely to cause problems. When the capabilities of the microphone are on a very high level, also the requirements for the test system and the test environment become more stringent. This is maybe the most evident when measuring the signal-to-noise ratios of very low-noise microphones. The challenge is the elimination of the many noise sources that can affect the test results. Noise to mitigate is, for example, ambient acoustic noise, ambient structure-borne noise, as well as the electrical self-noise of the measurement system. Ambient acoustic and structure-borne noise can come from a wide variety of sources. Building ventilation systems, cooling fans in electrical equipment, people moving and working in the building, office babble, traffic, and so on. The noise can be also production facility noise, if the measurements are done in the same building as microphone or device production. Ambient noise can be reduced by doing the measurements in an anechoic chamber or an anechoic box that eliminates external noise and also provides the measurement a reverberation-free environment. The efficiency of the noise elimination naturally depends on the specifications of the anechoic space. One key way to keep the noise level down is to avoid any equipment that causes acoustic noise in the space where the measurements are done. ambient structure-borne noise can be reduced with vibration isolation systems that can vary from a simple rubber base or an inflatable cushion under the measurement system to very sophisticated and thereby expensive solutions. The most efficient noise reduction methods tend to be big and heavy. A more modern noise mitigation method is to use an active noise cancellation system that senses the noise, which can be either acoustic noise or vibrations, and cancels the effects of the noise electrically. Sometimes the person doing the test must simply avoid noisy hours and do the measurements when things are quiet in terms of human noise or vehicle traffic or HVAC activity. There are several things that can be done to reduce the electrical self-noise of the measurement system. The first requirement naturally is that high-quality test equipment is used and that the self-noise of the system is low enough to be suitable for measuring the performance of the DUT. Key equipment is, for example, the amplifiers and the audio analyzer used in the system. The designs and quality of the filters, low pass and high pass, as well as awaiting filters used in the system can also affect the results significantly. Proper maintenance and frequent calibration of the measurement equipment is also very important to ensure high accuracy. Proper installation and setup of the measurement system is another key factor. For example, cabling and grounding must be done properly to avoid ground loops and other noise sources. It's also important to avoid electromagnetic noise sources in the measurement space, such as fluorescent lights, RF equipment, cellular devices, and so on. In noise measurements, it's important to note that the noise of the test system and the test environment must be significantly lower than the noise of the DUT microphone in order to avoid significant noise contribution to the test results from the system or the environment. In order to reduce the contribution of the test system down to 0.1 decibels, the noise of the test system and the environment must be 15 decibels lower than the self-noise of the microphone. With modern low-noise MEMS microphones, this means that the self-noise of the system must be around 10 dBSPL. The noise level of a typical office is somewhere around 45 to 60 dBSPL. This is way higher than the required 10 decibels, so it may take a significant amount of effort and money to reach the level needed for noise measurements. I talked more about sound pressure levels in episode 2. The electroacoustic parameters of a MEMS microphone can easily be affected by environmental factors such as temperature. Therefore, in order to do high accuracy measurements, the environment in the lab must be controlled and stabilized. This means regulating, or at least monitoring, all the factors that could affect the results, such as temperature and humidity levels, as well as air pressure. You can see a set of example limits for these variables in the table here. There can be, for example, two sets of condition limits. One for measuring the performance of the microphone in optimal conditions, the temperature around normal room temperature, 20 degrees Celsius. Another set of condition limits may be applied in tests that are done to make sure the device and the microphone operate on a good level in a wide variety of conditions, for example from 0 degrees Celsius up to 50 degrees. Within this wider temperature range, the requirements for parameters such as sensitivity may be loosened a little. Outside these limits, but within the limits for the operating conditions of the microphone or the device, the microphone must be operational, but the highest performance level is not required. The operating temperature limits may be, for example, from -20 to +70 degrees Celsius. Also, electrical factors, such as the exact supply voltage level, can also affect electroacoustic measurement results. Therefore, supply voltage limits must be included in requirement specifications and test results. The last, but certainly not least, thing to mention in relation to MEMS microphone measurement accuracy is the human factor. The personnel doing the testing must understand what they're doing and know how to conduct accurate measurements and avoid disturbances that could affect the results. The risk of accidental errors, such as typos and wrong commands, can be reduced by automating the tests. Measurement inaccuracies resulting from placement inaccuracies of the different parts of the system can be reduced with jigs that help the operator set the system up accurately and repeatably every time, regardless of who the operator setting up the system is and how tired he or she is. A key part of the electrical and electromagnetic capability verification of MEMS microphones is RF immunity testing. RF immunity can be specified and tested in several different ways. There are conducted RF tests, radiated RF tests, accessory-related tests, and so on. The idea in all RF testing is to expose the microphone or the microphone system to electrical or electromagnetic signals and check in the microphone output for disturbances. The immunity to conducted RF disturbances can be tested by injecting RF energy directly into the pins of the microphone and measuring the resulting demodulation level in the microphone output. Another way to test RF immunity is to place an antenna in the vicinity of the microphone in order to subject the microphone to radiated RF energy. This so-called near-field RF testing simulates the real-life RF conditions in a device, such as a smartphone. Device manufacturers also test microphones simply by putting them into devices or device prototypes, turning the antennas on full power, and checking the microphone signals for disturbances. Tests in real devices tend to give results that reflect the real world better than tests that only simulate the actual conditions in a device. There are also device-level tests for measuring, for example, how microphones in a headset connected to a device behave while the device is being charged. RF performance can also be simulated, but the correlation between the simulations and actual microphones and devices tends to be poor. One noteworthy aspect of MEMS microphone RF tests is their poor repeatability. It's very difficult to conduct RF testing accurately and repeatably, and so that tests done in one laboratory in one location would be comparable to tests done somewhere else with different equipment and by different people. There are many subtle variables that can affect the test results significantly. For example, the exact level of the radio frequency disturbance on the microphone is difficult to control. Even if the test procedures have been specified very precisely and equipment built exactly to the same specifications, the results may still not be the same because of all the variables that affect the tests. The variables are, for example, test equipment, test personnel, location of the antenna in relation to the DUT, test system cabling, properties of the antenna, and so on. Because of the poor accuracy and poor repeatability of RF tests, it's difficult to set absolute RF immunity requirements for microphones or microphone systems in devices. Therefore, some device manufacturers have given up on component-level RF immunity requirements and testing. Instead, they determine the acceptabilities of the RF immunities of the microphones they put in their devices in tests done in actual devices or device prototypes. Microphones manufactured by competing suppliers are used as performance benchmarks to each other. Let's have a look at some more or less standard RF tests used for MEMS microphones. The microphones can be tested either as bare components or as parts of device systems. The direct injection test is a component-level test in which RF disturbances are conducted directly into the contact pins of the microphone. The interference demodulated into the microphone output is then measured. If the disturbance level in the output remains within acceptable limits, the microphone passes the test. The test description and the pass criteria usually include a maximum level for the disturbances in the microphone output, as well as a frequency range, for example from 10 MHz to 2.1 GHz. The near-field radiation test is a component-level test that subjects microphones to electromagnetic radiation that simulates the antennas, signals, and radiation fields that you find in a cellular device. The antenna is placed close to the microphone, typically within a few millimeters. The interference in the output of the microphone is measured, while the antenna transmits RF energy onto the microphone via air. Again, the resulting disturbance level must be within acceptable limits. All the variables I talked about a minute ago must be minimized to enable getting meaningful results from the test. The locations of the antenna, the microphone, and the other parts of the system in relation to each other must be very accurate. A jig that determines the location of the antenna in relation to the DUT is recommended. TDMA noise is the typical cellular disturbance you may have heard on your phone, or if you have put your phone too close to a speaker. The TDMA test, more officially the 3GPP idle channel noise sending test, is a product level test that measures the interference induced into a microphone when making a call. The test is done by establishing a call with the phone's wireless transmitters on full power. The microphone output is then checked for TDMA interference, noise at 217 Hz and its harmonics. The audio breakthrough test is a test that looks for problems in the designs of the circuit board or the antenna of a device. The microphone is naturally a part of the test. The test measures the disturbances on a device headset microphone while the device is being charged. The test is done by injecting common mode RF interference via the phone charger. The injected interference has a 150 kHz to 80 MHz carrier frequency and it's modulated with 1 kHz 80% amplitude modulation. The interference then couples into the microphone of the headset and the 1 kHz demodulation level in the audio output is measured. The audio breakthrough test is a product-level radio frequency disturbance test that is required by ETSI regulations for devices sold in Europe. Okay, that's it for electroacoustic measurements, at least for now. As always, discussion and comments are very welcome, so please don't hesitate to participate. In the last two episodes of this series, numbers 27 and 28, I'll talk about the reliability testing of MEMS microphones. Thanks for watching, I hope I'll see you around. Cheers! If you have any comments or questions, write them down in the comments below and I'll do my best to answer them. You can also contact me online or on social media. If you like what you saw here, give a like for the video and subscribe to the MOSOMIC channel. That way you help me reach more people and thereby create more content. If you need more in-depth microphone training than what you saw here, contact me and we can arrange it. The training can be adapted to suit any interests and skill levels, and the customer can choose the location and duration of the course. MOSOMIC provides also consultation services in all things related to MEMS microphones. If you're a microphone buyer, I can help you select the right components for your product and manage your microphone suppliers. I can also assist in implementing the microphones into your device. For microphone manufacturers, I provide microphone marketing, product definition, product management, and development management services. I can also help you create all kinds of MEMS microphone documentation.